In our paper, DreamPose, Fashion Image to Video Synthesis via Stable Diffusion, we present a diffusion-based method for generating animated fashion videos from still images. Digital fashion is extremely prevalent today in online shopping and social media platforms. However, online clothing is often limited to still photographs, which do not capture how clothing drapes and folds as it's being worn. In contrast, fashion videos capture this valuable information while providing a more engaging user experience. Given an image and a sequence of human body poses, our goal is to realistically animate the input image using the sequence of poses, using a pre-trained text-to-image latent diffusion model called Stable Diffusion. This comes with several challenges. First, the pre-trained Stable Diffusion model is text conditioned, so it does not automatically support precise image or pose conditioning. Moreover, the exact fine-grained details of the input image must be preserved in each frame. Additionally, running Stable Diffusion frame by frame does not enforce temporal consistency across a video. We address these challenges by adapting the Stable Diffusion architecture and fine-tuning strategy. Our approach to pose conditioning is to concatenate 5 consecutive dense poses, along with the noisy input latent features to the UNet. These poses are centered at the target pose and are aligned with the target frame's noisy features. We found that this 5-pose representation yields smoother motion than a single pose representation, since the dense poses are prone to jitter that would make the resulting video also jittery. These inputs are iteratively denoised by the standard Stable Diffusion UNet, which is pre-trained on a large dataset for text-to-image generation. To replace clip text conditioning, we designed a novel image encoder consisting of 2 pre-trained clip and VAE encoders and a custom adapter module. We found that replacing the clip text encoder with a clip image encoder yields reasonable semantic fidelity to the input frame. But by adding the additional VAE embeddings, we increase the finer grain fidelity of the output frame. These 2 embeddings are jointly modeled using an adapter module before being passed to the UNet. We also introduce a 2-stage fine-tuning procedure to yield crisp garment and face details that are subject-specific. DreamPose is first trained on a full dataset of fashion videos, or more precisely, randomly sampled frame pairs from the UBC Fashion Video Training dataset. Then, in the second phase, this base model is further fine-tuned on a single specific input image, similarly to DreamBooth. While our model can be fine-tuned with an arbitrary number of subject-specific frames, we only require 1, and all of the results on our website and paper are generated from fine-tuning on just 1 frame, unless otherwise specified. With our method, we are able to realistically animate a diverse range of fashion images. For additional results, please refer to our project page. Our method also effectively animates images using poses extracted from a separate driving video. This implies that DreamPose can be used to animate any fashion image online using a generic pose sequence. While our fine-tuning strategy is effective for preserving details and identity, it does require an additional 30 minutes of extra fine-tuning on a subject with 2 GPUs, which may not always be feasible in real-world applications. We suspect that part of this is due to the limited size of the training dataset, which only contains a few hundred videos of female models in dresses. Additionally, our method sometimes exhibits incorrect garment details, minor pattern flickering, and pose inconsistencies. Here we compare our method to 2 state-of-the-art image animation methods, articulated animation and thin plate spline motion model. Overall, we find that our model exhibits better person and garment details, particularly with larger pose changes. Similarly, we quantitatively improve over both image animation methods and a recent pose transfer diffusion model on a variety of image and video metrics. Here we provide qualitative ablation of our method. Our multi-input pose representation significantly reduces minor motion flicker, particularly around the face and feet. We also find that fine-tuning the VAE decoder, in addition to the UNet, decreases high-frequency noise. Lastly, using VAE embeddings in addition to the clip embeddings improves the precise color of the garment and appearance of the person. Thank you for your interest in our paper. We invite you to check out the full paper as well as additional results, ablations, and comparisons at our project website.